Hi, welcome back all of you. Now we will discuss about the molecular shapes in the covalent compounds. In the covalent compounds, we can determine the shape of a molecule from the VSEPR theory, right? So the valence shell electron pair repulsion theory. Here, this theory will help us to explain the shape of a molecule. To get the shape of a molecule, basically we have two concepts. One is the VSEPR theory, the other one is hybridization. But right now I'm going to concentrate on the VSEPR theory, how to determine the shape of a molecule from the VSEPR theory. So according to this VSEPR theory, we need to first of all find the number of electron pairs around a central atom in a molecule. Let's say we have a molecule AB3 or AB4 type of a molecule. Here the central atom A, and we have to find out the number of bond pairs and the lone pairs around this central atom A in the molecule AB4. So from the number of bond pairs and the lone pairs, we can find what type of the geometry the molecule attains. Right, so first thing is we have to check the number of lone pairs and the bond pairs in the molecule. Let's take few examples here. Molecules with only bond pairs, right? So if you have a molecule without any lone pair, what will be the shape? Different shapes are possible. If you have an AB2 type molecule, then the shape will be linear. Here AB2 type means we have a central atom A and there are the two B atoms, and these two B atoms obviously they will get aligned at 180-degree angle, so the bond angle must be here 180 degree. Why these atoms remain at 180 degree? Because the electron pairs, the bond pairs here, they will repel each other, and this is the most stable geometry, this is the most stable shape that is possible for this linear molecule, because here the distance is maximum and the repulsion between the bond pairs is less, so there's maximum stability, right? So that means any molecule which does not have any lone pair on the central atom and there are two bond pairs, we can say the molecule will be linear. Example, we can say it is the beryllium chloride or beryllium hydride, right? BH2 molecule. Here the central atom is beryllium here, and there are two hydrogen atoms, and these two hydrogen atoms, these are linearly oriented, and the bond angle here is 180 degree because beryllium does not have any other electron pair around it. Now if you have an AB3 type molecule, then you have a trigonal planar shape. Central atom A and the 3B atoms, these are in one plane, just like a triangle, right? If you join this, so you get a trigonal shape, trigonal planar, because all the atoms here are in the one plane. The 3B atoms and the central atom A, these are in one plane, and the angle here is 120 degree. So the molecule, AB3 type molecule with 3 bond pairs and without any lone pair around the central atom, you can say the shape is trigonal planar, right? Trigonal planar. And again, example we can quote here is boron hydride, right? BH3. So here the boron has 3 electrons in the valence shell, and this boron, it forms the 3 bonds with 3 hydrogen atoms, 3 covalent bonds are there, and the molecule is trigonal planar shape because boron does not have any lone pair around it. It only has 3 bond pairs. This is the 1 bond pair, 2nd bond pair, 3rd bond pair, and the bond angle here is 120 degree in case of the boron trihydride. Another molecule is AB4 type molecule. If you have a central atom A and there are 4 B atoms around it, 4 B atoms around it, and they get aligned along the corners of a tetrahedron. Central atom A without any lone pair, only the bond pairs are there, so we can say the molecule will have a tetrahedral geometry, because if you join these these atoms here, if you join the B atoms here, what type of a shape you get? You get a tetrahedron, right? If I'm going to join these atoms, so the geometry that you get from this arrangement is a tetrahedral geometry. So that's why this is called as a tetrahedral structure to the AB4 type molecule. Again, the example we can quote here is the methane, CH4, carbon with 4 bond pairs without any lone pair around the carbon has got 4 hydrogen atoms, and the shape is tetrahedral. Alright, another molecule, AB5 type molecule, right? Here we have 5 bonds, have 5 B atoms around the central atom A, and again the atom A does not have a lone pair. Now the 3 bond pairs, 3 B atoms will be just like a trigonal planar shape. They'll be in the one plane. Here it is, right? So these 3 B atoms are in plane, and one of the B atom will be above this plane, the other one is below the plane, right? So that means you have a central atom A and the 3 B atoms are in one plane, and one of the B atom is above the plane, the other one is below the plane. So the geometry here that you get from this molecule is called as a trigonal bipyramidal, right? Trigonal bipyramidal, right? Because you got, you know, the two pyramids here. If you join this B here with these B atoms over here, you get a pyramid from the top and one more from the bottom, right? So that's why this is called as a trigonal bipyramidal. So that means a molecule with 5 bond pairs around the central atom A without any lone pair, the shape will be trigonal bipyramidal. Example we can say is the PCl5, Phosphorus Pentachloride. Here the phosphorus is having the 5 electrons, and these 5 electrons, they form the 5 covalent bonds with the 5 chlorine atoms, and the 3 chlorine atoms, they will be in plane like this, just like a trigonal planar shape. And this is one plane here, right, in which one phosphorus and the 3 chlorine atoms are there, and one of the chlorine is above this plane, the other one is below the plane. Interestingly, in this molecule you have 2 types of bond angles. You don't have a one bond angle, right? Linear, it is 180, trigonal planar, it is 120, tetrahedral, it is 109.5. Here in the trigonal bipyramidal, we have 2 types of bond angles. One is, 120 here, right? This is the atoms here which are present in this trigonal planar shape. The bond angle will be 120 there, and the one chlorine atom which is top and the bottom, that's going to form here the 90 degree. Alright, so in the trigonal bipyramidal you have a 120 degree bond angle and 90 degree bond angles, right? Another example is AB6 type of molecule. Central atom A, and around it there are 6 B atoms without any lone pair on the central atom A. The 4 B atoms here, they will be in plane, just like a square here. One B atom is at the top, the other one is at the bottom. So the shape here is called as octahedral shape, because if you join here these B atoms here, then you get a geometry with the 8 faces here, right? You get 8 faces. So this is the one face here, and if you join this one, this one, this one, you get another face, right? Here you get another one. This is the third one, and from the other side you get the fourth one. So 4 faces from the top and 4 faces from the bottom. Example here will be sulfur hexafluoride, SF6. Central atom sulfur, it has 6 electrons. It forms 6 covalent bonds with the 6 fluorine atoms. So there is no lone pair around the sulfur. Only 6 bond pairs are there, and the 4 sulfur and the 4 fluorine atoms, they'll be in one plane, just like a square, with the bond angle 90 here, right? The bond angle is 90 degree, and these 4 fluorine atoms, the central atom sulfur, these are in one plane. Now one of the fluorine is above the plane, the other one is below the plane, right? So this is called as an octahedral because you get 8 faces. Like suppose if I join this fluorine, this one and this one, right? So I'm gonna get a one face here, one plane. This is the one plane, and you get here from this one another plane. Basically you get the 4 planes from the top and 4 from the bottom. So there are 8 faces. That's why this is called as an octahedral. All right, now let's take certain examples in which we find both the lone pairs and the bond pairs. All right, let's take here an example of a sulfur dioxide molecule, SO2 molecule, right? So sulfur has 6 electrons, and it actually forms a double bond with oxygen, another double bond with another oxygen, and this sulfur has one lone pair of electron. So around the sulfur here, the total number of bond pairs actually are 3. For example, if you have a trigonal planar shape, you have a central atom A and there are 3 B atoms, right? 1, 2 and the 3, right? This is the third atom. Imagine if you replace this bond pair here by a lone pair. You don't have a bond pair, you have a lone pair now. Okay, we have a lone pair rather than this bond pair. So what will be the geometry of this molecule? Alright, the geometry will be a band shape. You have atom A and there are 2 B atoms now, and there is a lone pair of electron on the central atom A. This is not now a trigonal planar shape, right? This is not a trigonal planar shape, this is a band shape, right? So sulfur dioxide has a similar structure. Sulfur, it has, a double bond with oxygen, another double bond with another oxygen, and it has a lone pair of electrons. Remember, if you have a double or a triple bond between the two atoms, right? If you have, suppose you have an atom A, it is bonded with atom B through a single bond, or it is bonded with a double bond, or it is bonded with a triple bond. We treat it as a one electron pair, right? This is as a 1 electron pair, this one as a 1 electron pair, and this one also as a 1 electron pair. So this one, the double bond here, we treat it as a 1 electron pair, bond pair, this one as a 1, right? So that means around the sulfur there are 2 bonds, 2 bond pairs and a 1 lone pair, and the shape must be not a trigonal planar, it's a band shape, right? It's a band shape. Now another example of the tetrahedral. For example, from the tetrahedral structure, if I replace one of the bond pair by a lone pair, what will be the geometry then? Suppose you have an atom A, it is attached with the 4 B atoms, then the normal geometry will be tetrahedral. But right now I am going to replace this bond pair by a lone pair. Then the geometry will be not a tetrahedral, it will be a trigonal pyramidal. This is the central atom A, these are the 3 bond pairs, and this is now a lone pair here, right? The geometry is not a tetrahedral, it is a pyramidal shape, right? It is a pyramidal shape. An example of a pyramidal shape is ammonia, NH3. Nitrogen with 3 hydrogen atoms, and it has a 1 more electron pair also, a lone pair also there with the nitrogen. So that means this ammonia is pyramidal in shape. It's not a tetrahedral, rather it has a pyramidal shape, right? And what if we have, suppose, a molecule and in which you're going to replace 2 bond pairs now by the 2 lone pairs, okay? A tetrahedral shape, and suppose you're going to replace this bond pair by a lone pair and also this one by a lone pair. So that means the geometry will be not a tetrahedral, not a pyramidal, it's a band shape again, right? We have a central atom A and 2 B atoms there, and there are 2 lone pair of electrons also. The shape is not a tetrahedron, right? Basically you are replacing this one and this one by a lone pair. So the geometry is a band shape or angular shape. Example we can quote here is water, H2O. Oxygen has 2 bond pairs with 2 hydrogen atoms, and it has also 2 lone pair of electrons. So therefore the shape is a band shape or an angular shape, right? This is a band shape. Hope you got the concept. Thanks for watching the video. Bye for now.